All right, let's jump right into this explainer and peel back the magical layers of programming to see the actual physical real estate of computer memory. When we write code, it's incredibly easy to stay up in the clouds, thinking purely in abstract logic, variable names, and fancy algorithms. But beneath all of that software abstraction lies a very physical, very rigid world of hardware. Today, we're going to look at how your code actually lives and breathes inside your computer's RAM. Here's our roadmap for today's explainer. We're going to look at variables and memory addresses, stack versus heap memory, arrays versus linked lists, how Python handles memory, and finally, alignment, padding, and packing. Let's get to it. Section 1. Variables and memory addresses. Let's start at the absolute micro level. You know when you type x equals 5 in your code? It kind of feels like magic, right? But what you're actually doing is acting as a real estate developer inside your computer's RAM. Modern computers have gigabytes of memory, and you can literally think of this main memory as this massive, sprawling array of individual bytes. And every single byte, it has its own unique physical location. Which brings us to the memory address, a unique fixed hardware location in main memory. It's basically a house's street address, where your variable data lives. The absolute core concept to grasp here is that the address is fixed. Think of your variables as houses along a physical street. The address doesn't change, right? People use it to find the house. It's a hardware property. But the contents, the occupants actually living inside the house, well, they can change or vary over time. The lot stays exactly the same, but who rents it? Totally up to your code. So a variable is really just a named location with 3 distinct parts. First up, the name. That's just the abstract label that you, the programmer, assign to it. Second is the content, often called the R value. This is the actual data stored inside, like the number 5. And third, the address, or L value. This is that fixed physical location mapped by the compiler. And here's the crazy part. When your program actually runs, the computer drops your nice little names entirely. It manipulates all that data strictly by these physical memory addresses. And that brings us to a concept that, let's be honest, terrifies a lot of new programmers: pointers. A pointer is a type of variable that stores the physical memory address of another piece of data. The crucial thing to remember is that a pointer doesn't hold standard data, like a number or a word. Its one and only job is to point you to a specific street address. It's a variable whose content is literally the memory address of another variable. So it's not the house itself, it's the map to the house. Section 2. Stack versus heap memory. Let's explore the 2 very different neighborhoods where your code can actually rent space. Whenever you run a program, memory is typically split into 2 main areas: the stack and the heap. The stack is like a highly organized short-term rental market. It allocates memory automatically in contiguous blocks for your local variables every single time a function is called. And then bam, freeze it immediately when the function ends. It's incredibly fast and thread-safe. Now, the heap? The heap is a sprawling, dynamic cityscape that needs active management. It allocates memory in a random, fragmented order. It's slower, it's shared among all threads, and it requires either manual deallocation, like you'd see in C or C++, or a garbage collector, like in Java or Python, to clean up unused memory so you don't get memory leaks. This contrast is perfectly highlighted when we look at primitive types versus reference types in languages like Java. Primitive types, like your basic integers, store their actual values directly in that highly efficient stack. But reference types, like objects or arrays, they're just too complex for the strict rules of the stack. So the actual object gets built out in the sprawling heap, and the stack just holds a reference, a pointer, that maps to that object's address in the heap. So if you copy a reference variable, you aren't actually duplicating the object. You're just giving 2 different stack variables a map to the exact same house in the heap. And this is exactly why changing an object in one part of your code can accidentally mess it up everywhere else. Moving on to Section 3, arrays versus linked lists. Let's see how we build larger communities of data. Think of an array as a rigid cul-de-sac. It's stored as one single, continuous, unbroken block of memory. And because of this setup, it gives you instant, constant time or O of 1 access. If you know the starting address of the array, the computer can instantly calculate the exact physical address of any element inside it. But, this rigidity absolutely comes with a cost. What if you want to add a 5th element, but the memory slot right next door is already occupied by something else? Well, you're stuck. And this is exactly where linked lists come in. If an array is a rigid cul-de-sac, a linked list is a scavenger hunt. Instead of one contiguous block, a linked list scatters its data wherever it can find an empty lot in memory. Each piece of data lives in a node, and for every single node, you have to store not just the data itself, but also an extra pointer that holds the exact address of the next node in the sequence. Because they're scattered all over the place, you can't just magically jump to the middle of a linked list. You actually have to start at the head and visit every single house sequentially to find the one you want. That takes O of n time. So we are looking at a massive trade-off here. Arrays give you instant access, sure. But if you want to insert a new item at the very beginning, you literally have to physically shift every single neighbor down one slot just to make room, which is incredibly slow. On the other flip side, linked lists are slow to search, but inserting a new item is practically instant. You just grab an empty lot anywhere in memory, update a couple of address pointers to link it into the chain, and you're done. All right, section 4, Python memory and lists. Let's move to a higher level language and see how Python plays by its own real estate rules. In Python, the whole concept of variables takes a really fascinating twist. When you type a equals 2, Python doesn't just put the number 2 inside a box named a. Instead, Python finds a spot in memory, puts the number 2 there, and simply makes a name tag pointing to that address. Because variables are essentially just name tags pointing to memory addresses, if you set list1 equals list0, you are not copying the list. No way. You are just printing a second name tag and pointing it at the exact same physical house in memory. We call this aliasing. Even when you pass a list into a function, you're just passing the name tag, not a copy of the actual data. And this is exactly why modifying a Python list affects all aliases. They are all looking at the exact same house. We say lists are mutable. But interestingly enough, things like integers and strings are immutable in Python. You literally cannot change the underlying value of an integer in memory. If a points to 2 and you type a equals 3, Python doesn't change the 2 into a 3. Actually, it finds a brand new address, puts a 3 there, and moves the a name tag to point to that new address. Here's another cool fact. Python lists aren't technically standard arrays, and they aren't linked lists either. Python lists give you this illusion of infinite space by secretly renting a much larger plot of land than you actually asked for. They hold a buffer of extra space. This lets you append items instantly, in O of 1 time. But the moment that buffer maxes out, Python hits the panic button. It finds a brand new, much larger plot of contiguous memory elsewhere, physically copies every single item over in O of n time, and then updates your name tag. It literally moves the whole house when it gets too full. Section 5, Alignment, Padding, and Packing. Finally, let's check out the strict architectural building codes that dictate memory layout in lower-level languages like C and C++. Now, you might be wondering if you put a 1-byte variable and a 4-byte variable into a data structure, it should take up 5 bytes of memory, right? Well, it rarely does. Your CPU doesn't read memory byte by byte. It reads in fixed-size chunks, or words, usually 4 or 8 bytes at a time. If a piece of data sits right across the boundary of 2 words, the CPU has to work overtime, performing multiple fetches just to piece it together. To avoid this catastrophic performance slowdown, the compiler enforces what's called structure-member alignment. Picture a structure with a 1-byte character, followed by a 4-byte integer, followed by another 1-byte character. Basic math says that's 6 bytes. But the compiler puts the first character in, then realizes, wait, the integer needs to start on a multiple of 4 to keep the CPU happy. So the compiler secretly injects 3 blank, totally wasted bytes, called padding, just to align the integer. Then it places the integer. Then the final character. And finally, it tacks on 3 more padding bytes at the end, so the whole structure size is a multiple of 4. Boom! Your 6-byte structure now takes up 12 bytes of physical RAM. Now, if you're programming an embedded device or an IoT gadget where literally every single byte of RAM is precious, this invisible waste is just unacceptable. You can actually force the compiler to strip all this padding out using a technique called data packing. But remember, memory management is always a game of trade-offs. You gain back your space for sure, but the trade-off is a massive hit to your execution speed because the CPU now has to struggle with unaligned memory reads. So what if you want to save memory without sacrificing that precious speed? Well, the best trick is surprisingly simple. Just reorder your variables. If you define your structure by arranging the members from the largest data type down to the smallest, you naturally eliminate those gaps. Place the 4-byte integer first, then the 2 1-byte characters. The compiler groups them perfectly, adding only 2 bytes of trailing padding at the very end. You've just shrunk your structure from 12 bytes down to 8, while keeping your CPU running at absolute maximum efficiency. And that really brings us full circle. Every variable you declare, every list you append to, every object you instantiate, they are all physical tenants in the sprawling real estate of your computer's RAM. The compiler maps every single abstract name you write to a unique, rigid physical memory address and bakes that address right into the machine code. Understanding this physical reality completely transforms your code. You stop just writing abstract instructions and you start architecting optimized physical layouts in memory. You control the stack, the heap, the pointers, and the padding. So I'll leave you with this to ponder. The next time you simply type x equals 5, what unseen physical architecture are you actually commanding? What kind of real estate developer will you be? Thanks for hanging out with me for this explainer, and keep building.